I would like to spend a couple of lectures talking about hypothesis testing and just do a review of it to kind of get our feet settled again. So anyways, remember that the setup looks something like this. For any kind of hypothesis test, you have an H sub 0 and then you have an H sub A. H sub 0 being the null hypothesis and the H sub A being the alternative hypothesis. We're going to focus on the mean, so this is what our hypothesis test will look like. I might have something like mu is greater than or equal to some number m, but then the alternative hypothesis would force it to go the other way and say mu is less than m. Anything that has an equal attached to it is in the null hypothesis. So if I were to go mu, say, is less than or equal to m, then for the alternative hypothesis, we have mu is greater than m. And similarly, if I have mu equals m, I put not equals, but I meant to put equals, or mu does not equal m. So the null hypothesis gets the equal signs, the alternative hypothesis gets the inequalities. The claim may be either the null or alternative hypothesis depending on the problem at hand. And we'll do a couple of examples. So the first step is to set up that. Next, we must specify a level of significance. And then typically, we'll do a graph of the standard normal distribution. So that's the one. Well, you know what these things look like. It doesn't matter what if it's standard or not. Any normal distribution will look like that. This is the one that has a mean of 0. Once you have the alpha, you'll know, if we're going to shade over here, maybe that amount of area is alpha. Or if we shade on the other side, maybe that is alpha. Or if both of them. It just depends on the problem at hand. Next, we'll be calculating the test statistic. And that's something that looks like this. The beginning of this region we'll call z sub 0. And for our z value, we'll do something like x bar minus mu divided by sigma over the square root of n. So this is why it's standardized, because of that. So you calculate that, and that will determine whether you're going to be in the shaded region or not. Now, one thing they did, we're going to do a couple of examples, one of each kind for these, but we are going to then find the p-value. This is sort of a newer thing that's being pushed by the statistical community, and we are going to focus on doing most of the problems that way, but I'm going to do the first couple of problems in two ways so that you can see one way you might have done, and then one using the p-value so you can compare. And then finally, we're going to make the decision. That's whether to accept or to reject H naught. And what's nice about this is once you have a p-value, is you can simply look at the p-value versus alpha. So if p is less than or equal to alpha, we are going to, let's say that's true. If p is less than or equal to alpha, we will reject H naught. However, if that's not true, we will fail to reject H sub 0. I'm not exactly sure why they don't just say we accept H sub 0, but fail to reject it is a little more scientific in that it's this the notion here is that this is evidence that suggests that something is true. It's not guaranteed true. It just provides statistical evidence that says that chances are what we're trying to say is true or false. All right, suppose I have a claim that the mean of something is greater than or equal to 1475. And what I have, we know from a population that is normally distributed that sigma is equal to 29. So let me write that down. The population is normally distributed. So we need some other information. So I have, anyways, the sigma is known in this situation here. I have a sample that looks like this. The mean of that sample was 1468. And the number of people, or the number of items in the sample, I don't really know what this was equal to 26. So what we want to do is test the claim at alpha equals 0.07. All right, so the first thing I'm going to do is called the classical method. And you'll see what I'm talking about. Let's start with alpha equals 0.07. Oh, actually, before I do that, no matter what you do, you need to state your null and alternative hypothesis. Since the equal sign is attached to mu in the claim, then that's part of the null hypothesis. So I'll have mu is greater than or equal to 1475 since it has the equal sign. That's the claim. You don't have to write that part, but that is part of it. And then h sub a will be the inequality that points in the opposite direction. So you'll have mu is less than 1475 as the alternative hypothesis. What this does is we're ultimately going to have a left-tailed test. The inequality points to the direction of the test. So in this case, since it's pointing to the left, we're going to use the left-tail method. So start with our alpha equals 0.07, and then use your table, your normal distribution table, to give me on the standard normal distribution what the z-value is that corresponds to that. So if I'm using alpha equals 0.07, most normal distribution tables will start from 0 and go to infinity, which means they're only dealing with 50% of the whole curve. So most of them are built that way. So if I want to look on the table, for the table, I'm going to need to do this calculation, 0.5 minus 0.07, which equals 0.43. Now come to the table. All right, let's see, we're going to go to, so I'm looking in 0.43 into this region here. Let's see if I can find, okay, what I have here, if you can follow the pen, I have two markings, 0.4292 and 0.4306. The closer one is the 0.4306. So let me follow what z value that corresponded to. I have 1.4, and then I look up 8. So come back to our notes. Z, I'm going to call it z sub 0, equals 1.48. That's not true. If this were a right-tailed test, that would be true. Since it's a left-tailed test, I need to put a negative in front of it. So this is my situation that I have. Now I'm going to calculate my test statistic. Notice I called that z sub 0. That's kind of how I keep track of things myself. My z value will be the test statistic. So let's do that next. So here, this is where you go z equals x bar minus mu all over sigma divided by the square root of n. In this case, the mu that we are testing is the 1475, and the mean that we got from the problem was 1468. and sigma is 29 and n is 26. This is approximately negative 1.231. And so where's that at? If I look at this graph, negative, so that's somewhere to the right of it. So this guy right here is not in the shaded region. So in a situation like this, we fail to reject. So we can see from the problem here, if that z value had landed in the shaded region, then we would reject h sub 0. Now I'm going to do a do-over using p-values. So let me throw the stuff that we had in there again. So we'll approach it as though we're doing the problem again. So the claim was that mu was greater than or equal to 475. We had sigma was equal to 29, x bar was equal to 1468, and n was equal to 26. Now this is a little bit different than before. Alpha equals 0.07 is our level of significance as before. So in this situation, it's a little bit different. We're going to once again calculate the stat as we did before. So I'll put this so it's complete. And that was 1468 minus 1475 all over 29 divided by the square root of 26. Negative 1.23. Now you only need to go to 2 decimal places because I'm going to now use the table to tell me how much area there is to the left of negative 1.23. However, unfortunately, that table only works with positive values, so I'm going to get a positive answer that I need to translate to the negative side. So let's go ahead and pull up the normal distribution table. And let's find 1.23 on the table. So I'm going to start with the row that is 1.2, and I'm going to move, it grew, I didn't mean to make it bigger, but probably doesn't hurt to do that. 1.2, and then I'll go to that. So I get 0.3907. The table gives us 0.3907. So let's write this down, table 0.3907. Now you got to remember what the table gives us. If we draw the normal distribution graph, what the table gave me was the area between negative 1.23 and 0. That's not what I want. The p-value that I want is over here. So in order to make use of that, I am going to have to subtract from 0.5. So we have p equals 0.5 minus 0.3907, and I get 0.1093. There's my p-value, and let's compare that to the alpha. Alpha, as you recall, is only equal to 0.07, and so we can see that p is greater than alpha, so we fail to reject H naught. This time our claim is that mu is less than or equal to 22,500, and the known population standard deviation is 1,200. And my stat that I got from the sample stat, or the sample mean, is 23,500. And the size of the sample was 45. Now we want to test the claim at alpha equals 0.01. All right, so first, once again, I'll do the classical method. And let's go ahead and calculate the test stat. Well, you know what, before I do that, let's do this. Let me write the hypotheses down. Since the equal sign is attached to the claim, that goes in H sub 0, so mu is less than or equal to 22,500. That is the claim. But then for the alternative hypothesis, now it's going to be greater than 22,500. And so this is what I'm going to test, whether it's true or false. Let's go ahead and get alpha equals 0.01. Give me the z sub 0 value. Once again, I have to do the same thing as I did before. I need to do 0.5 minus 0.01, which equals 0.49. So I have to go to the table and find the z value that corresponds to 0.49. Since this is a right-tailed test, everything's positive. So I can use the table at face value. All right, let's see. 0.49. I'll try to do it before. Let's see if we can follow here. 0.49. No, not quite yet. And once again, I have two values that I'm in between, so I'll choose the closer one. So I have 2.3. It looks like 2.33. So once again, it's not a bad idea to draw this thing. The more of these draw, the better the easier these problems get. Remember, this is the standard normal distribution. 2.33 is quite a ways out there. And now let's go ahead and calculate our test statistic. I recommend drawing this formula every time, and then it won't make it seem like you're memorizing it. I get a little reckless, so please bear with me. All right, our mean that we got was 23,500. That was the sample mean. Population mean that we're testing is 22,500. Let's see, where was our sigma is 1,200 and the n is 45. This is approximately 5.590. Which, if you look at this, is way, way in that region. Somewhere all the way over there. Since it's in the shaded region, we reject H sub 0. I want to redo the last example again. But this time, of course, use p-values. So let me get the relevant information down. We had H sub 0 was mu was greater, less than or equal to 22,500. If you remember, that was the claim. And then the alternative hypothesis made this into a right-tailed test because of that. Let's see, what did we have? We had sigma was equal to 1,200. The mean of the sample was 23,500, and n was equal to 45. And then finally, we were testing the hypothesis that alpha equals 0.01. First, let's calculate the test statistic. So we're going to have z equals x bar minus mu divided by sigma over the square root of n. And we have 23,500 minus mu, where'd you go? Mu 22,500. I know I just did this, but it doesn't hurt to do it a bunch of times. So then we have sigma was 1,200 over the square root of 45. And we already did this calculation, 5.590. Now, we go and look at the table. So, let me write that down. That's going to be the area to the right of 5.590. I don't even know if the table goes that far. Let's see. It does not. So we may assume that it's essentially, the p-value is essentially 0. Not quite, but it's beyond this table. I can see that it's going to be less than 0.0002. I know that about it, so let me come back to here. And p is, forget about being equal, p is less than 0.00, how many zeros were there before I had a 2? 499, so 0.002. So, and now alpha was equal to 0.1. So which of the two is bigger? Well, it's quite clear that p, being that small, is less than alpha. So in this case, we reject h sub 0. I wanted to do one last example that used a two-tailed test. So I'll do the same thing as before, the classical method and the p-value method. Let's say we have a claim that mu is equal to 6.3. Sigma equals 2.5. We have a known population that is normally distributed. That's the underlying assumption for all of these problems that I'm doing, is that we have a population that is that way. The sample stat that we have was that x bar equals 7.2 and test at alpha equals 0.05. So as I mentioned, the classical method comes first. Let me get my hypotheses. So my null hypothesis is going to be mu equals 6.3, and then my alternative hypothesis will be mu does not equal 6.3. So this, of course, is a two-tailed test. Now you might remember that when you have a two-tailed test, you have alpha equals 0.05, but then alpha over 2 equals 0.025. So then alpha over 2 is what we're actually going to be looking at. So go to the table with alpha equals 0.025. And I believe this comes out to 0.475. And let's go to the table. All right, 0.475, oh, right there, 1.96. So across from 1.9, and this is exactly right there, so that's a nice number to have. So in reality, we have a z sub 0 equal to plus or minus 1.96. So when you draw a picture of this, and of course the mean is 0 in the standard normal distribution. Now let's do our test stat. X bar was given somewhere here, 7.2. The mu that we got as a test is 6.3. Sigma, where did you go? Sigma is 2.5, and our N, I have yet to give you. So let me append it in the problem. I apparently forgot it. N was equal to 33, and let me put that in here. 2.068, and if you look, 2.068 is right into the right portion of the region, so that means we reject. Finally, let's redo the last example. With p-values. All right, let me write down all the information that we had. We had our h sub 0 was that mu was going to equal 6.3. Our h sub a was that mu does not equal 6.3. And then we had a a sample stat that was equal to 7.2. The number of people in the sample was 33, and the sigma, the known population parameter, was 2.5. So the first thing we are going to do is take a look at our test statistic, and we're going to have x bar minus mu divided by sigma over the square root of n. X bar was 7. Well, I know I did this, but I'm redoing it anyways. Just in case you only wanted to study the p-values, perhaps you could just look at the second part of every example. 2.5 divided by the square root of 33, and that was approximately. Now, since you're going to use the table, you don't need to go any more than 2 decimal places. So 2.07. Now, this inevitably, the z-value is going to end up on one or the other side. What we now need to do is go to the table, look at 2.07, and see how much area there is to the right of 2.07. So let's take a look. So 2.0 2.07 is 0.4808. So the table gives me 0.4808. So the table, we get 0.4808. What that tells me though is this is what the table gave me this. So that's not what I want. I want that part. And then we're going to compare that to alpha over 2 when all is said and done. So what I need to do then is take 0.5 minus 0.4808, and what do I get? 0.0192. And so where is our alpha? I don't remember what the alpha was. Alpha was 0.05. And so alpha over 2 was equal to 0.025. Let's compare. Which of these is bigger? I'm doing 0.192 versus 0.025. It looks to me like, if I get my decimals correct, I could actually do a good comparison. 0.0192. We see that the bottom number is bigger. So we see this was alpha, and that is p. So we see that p is less than alpha. So we reject H naught.